We've talked about the movement of ions in and out of one section of membrane that give rise to the action potential. And that's happening again at one little patch of membrane. We're now going to talk about how that electrical signal is transferred down the axon. So we need to go from the cell body down to the axon terminals. That's action potential conduction, that movement down the axon. So let's start with this by drawing a picture of a neuron again. And then looking again, so far we've looked at one small little place right here. And where is that place? The axon hillock, right? That's where all action potentials are initiated. And that's kind of where we've focused on the movement of ions, sodium in and then potassium out is what generates the action potential. However, now we want to look at what makes that move down. So again, we've got sodium flowing in, right? Why? Well, we had an initial stimulus that was large enough to cause some depolarization. That depolarization caused more voltage-gated sodium channels to open, and that's an all or nothing phenomenon where once voltage-gated sodium channels are opening, more and more are opening until we reach that plus 30. When this sodium flows into the cell, what happens to it? It diffuses, right? It's going to move, it's going to just spread. And it's going to spread in both directions, both this way and this way. Now, I'm just going to tell you for now that an action potential only occurs in this direction. They cannot go backwards. And we'll talk about why that is. Right now, I just want to look at what this movement down is going to do to the neighboring membrane. And what it's going to do is depolarize it. As this sodium moves this way, it's going to depolarize the adjacent section of membrane. And that's going to cause threshold to be reached at the adjacent section as well. So let's look at this in more detail. Here is a schematic of a neuron. Initial segment here, that's that axon hillock. And that initial segment, we're saying an action potential has been generated. Right, so there was some stimulus that was large enough to cause depolarization to threshold, boom, plus 30. So the membrane potential, the initial segment depolarizes to plus 30. What happens to those ions? They start to spread to the next door segment. So that's going to cause this segment next to it to start to do what? To depolarize. What number might you have here? And what number might you have here? So minus 60 is going to be less negative as this local current spreads. The segment beyond that is still at rest. It hasn't been affected yet. This minus 60, what's that going to do? It's going to cause voltage-gated sodium channels to open, and sodium's going to flow in more here. So that's what's happening here. An action potential develops in segment 2 due to this sodium rushing in that was due to that local current inside the cell. What's this membrane potential? Plus 30. That's when the action potential, ultimately it's going to reach plus 30 when the action potential is fully happened. So again, local current causes the depolarization enough to open more voltage-gated sodium channels. Positive feedback is what that is. More voltage-gated sodium channels opening, more voltage-gated sodium channels, more sodium flowing in, all or nothing phenomenon of that action potential reaching plus 30. These sodium ions are going to diffuse next door, and they are going to cause segment 3 to depolarize. So here we've got minus 60, and then ultimately, eventually, plus 30. Boom, all or nothing. And this is not a question of does this reach the threshold or not. Because the axon is so thin, this current is enough to cause the adjacent membrane to depolarize to threshold, period. Okay, so that's how an action potential moves down the axon. What's cool about this setup is it also allows for it to move only in one direction, and that's due to sodium channel inactivation. So here is another example diagram of the axon, and that sodium flowing in And again, the sodium's flowing in and diffusing in both directions, both downstream, down to the, so this is going to be the cell body over here, and the axon terminal is at the other end. But it's going to diffuse both ways. It cannot open voltage-gated sodium channels over here. Why not? Because they're not just closed, they're inactivated. And that's the important, that's why I told you that they inactivate at positive 30. These sodium channels are inactivated, so they cannot open again. So the sodium's only going to have an effect this way. That's what's shown here. Sodium, more sodium channels are then going to open due to that spread. And that unidirectional conduction is due to that transient inactivation of the sodium channels that we just passed by. So that inability of them to reopen when they're inactivated, you can't open something that's inactivated. It ensures that action potentials only conduct in one direction, from that initial axon segment by the cell body, the axon hillock, all the way down to the axon terminal. So it's a kind of a downstream way. And because this is actively propagated, right, we've got the opening of voltage-gated sodium channels over and over again. It does not fade as we go down. It is propagated in all or nothing matter down the entire axon. Okay, let's look at what this refractory period looks like on this graph here. So this graph should not look too scary right now. This is memory potential over time, and the movement of ions causes this peak and then hyperpolarization of the membrane of one location. And these are the ion channels that are open or inactivated at each time point. What I want to refer to right now is the absolute refractory period. That's what I just showed you. That was that refractory period that it's due to sodium channels that are open, but they're inactivated. So as we reach this, during this time point right here, you cannot open voltage-gated sodium channels either again or anymore. This is a time when another stimulus does nothing. So no matter how much you stimulate this neuron, you cannot have another action potential generated during this time. That's what refractory period means, a time in which another action potential cannot occur. And this is due to this inactivation gate down here, which means that even once we're like right here, you can't open those sodium channels again because they're inactivated. It takes this hyperpolarization to move that inactivation gate so that the sodium channels are back at the resting state again, where they're closed but able to be opened. So the difference between closed and inactivated is important. The other refractory period here is the relative refractory period. This is not an absolute refractory period. It is due solely to this hyperpolarization. What this means is a stimulus at this point would not be able to do as much. It would take a larger stimulus to create a new action potential. So this refractory period is when the potassium channels are still open. That's what's causing this hyperpolarization here, potassium flowing out. That causes hyperpolarization, and that means that you would need a really huge stimulus to cause another action potential at this time point. So at like 3.5 milliseconds, a normal stimulus, just regular sized one, like this, might not cause another action potential. It would take a larger stimulus. And that is the relative refractory period. Okay, let's do a quick learning check here. First of all, this diagram here is another way of looking at this. And so this is showing excitability on the same graph as well as the action potential itself, sodium movement, and potassium movement. And that's due to those ion channels being either open, closed, or inactivated. I like this diagram because it also incorporates up here both the opening of the sodium channel the inactivation of the sodium channel, and then here is where that sodium channel is able to be opened again. Here, excitability, it's high at rest. That means the ability of the cell to fire, to have an action potential, is 0 during the absolute refractory period. You cannot initiate another action potential during that time. And it's slowly increasing due to what? Because we have the hyperpolarization that's slowly going back to rest. So, answer these questions. The absolute refractory period is due to sodium channel inactivation versus the relative refractory period is due to hyperpolarization. And that's why it slowly increases back to high excitability at rest. So this would be once we're back to the resting membrane potential.